Welcome back to Lecture 10 of Applied Machine Learning. We are now at part 2. In this part, I would like to now use the Lagrange theory that we saw in the previous video and apply it to support vector machines. In order to do that, let me reintroduce a little bit some of the notation that we have defined in the previous lecture. And let's quickly remind ourselves what an SVM is. So remember that we are in the setting of binary classification, where we have a training data set of inputs and targets, and these targets take one of two possible values, +1 or -1. So this is the binary classification regime. And we are working so far with linear model families, which are families of which are models of this form. And here again, y equals -1 or 1. This is our target. And we can write this linear form in a succinct way using the vector dot product between theta and x. And here we distinguish between the intercept theta and the targets and the main vector of parameters theta. And we're going to see shortly why. Our goal here is to find a good linear model, a good boundary between the classes that will distinguish between the two targets. And at the very beginning of our lecture of SVMs, we defined this concept of margin, which is the distance from any point to the decision boundary, or to the separating hyperplane, as it's also called. And this distance, we can derive a very succinct form for it. We can derive the following formula, and this again exactly corresponds to the distance between the point xi to from the point xi to the separating hyperplane, and we denote this by gamma, and we call this the margin. And the principle that we want to enforce is that we want to find hyperplanes with large margins, which means that they fall in they separate the two boundaries, they separate the two classes, but they're also placed in a location that is as far as possible from any of the neighboring points. So it separates the 2 points and it places them as far away as possible on each side of the boundary. And the SVM is an algorithm that optimizes for the optimal margin. And we have defined the following optimization problem, which is a reformulation of a more intuitive way of defining this problem, where we're simply optimizing over the margin gamma. We started with that problem, and then we went through a series of mathematical transformations to derive the following quadratic problem, whose solution was equivalent to that of the first problem with which we started, but in this case it's a quadratic form that's easier to solve, and so this is typically the constrained version of the support vector machine problem. Here, this constraint ensures that every point is classified correctly, and its target is at least, its prediction, its score is at least 1 or -1, which are our two classes, or it could be even higher than 1 or lower than -1. And under this set of constraints, we're looking for the vector theta, which has the smallest norm. This is a constraint version, this is a constraint optimization problem. And in the previous video, we saw that whenever we have a constraint optimization problem, we can also formulate this as a unconstrained version with penalties. And then we can define the following primal Lagrange form in which we have added constraints as penalties, and we're optimizing over, we're basically minimizing a function of theta, which is this thing. This is a function of theta. We're minimizing it, but this function of theta is now itself an optimization problem over the lambda, and we have seen that the solution to this problem here, the minimum of the primal Lagrange form, is the same as the minimum of this constraint objective function. By the way, I just want to add here, I haven't mentioned this in the previous video, but this form, so in practice, we would not use optimization solvers for this expression. This is more of a mathematical form. It's an interesting mathematical fact that is used then to derive other optimization formulations that are actually solved, but this is actually not something that is, this is not a formulation that is used directly for solving for solving an optimization problem, but it's an interesting mathematical fact that can be used to derive other optimization algorithms. As I mentioned, these two forms have the same optimum, and so now I would like to use this Lagrange theory and I would like to apply it to the SVM problem. And the first step for that is to define a Lagrangian. So consider the following objective, and this is our Lagrange, our Lagrange multiplier, our Lagrange objective, in which we have Lagrange multipliers lambda. Again, this is the objective, and I have added these constraints with these Lagrange multipliers. Now, in the previous video, I defined this concept of Lagrange dual, and given a Lagrangian, we can optimize its primal form, or we can take the primal form and we can flip the max and the min to have them, instead of being first the min then the max, we can flip them and have first the max and the min. And now this becomes an optimization function over lambda, and this optimization function is called the dual. We can always construct this dual. So let's now apply this and construct a dual for the optimization problem, for the Lagrangian of the SVM problem that we had earlier. So recall that the Lagrangian it has this form, and we want to be optimizing this Lagrangian. We want to be minimizing we want to be maximizing the minimum over theta with this Lagrangian. So here on the next slide, I'm going to define what d over lambda is, and d over lambda is the thing that we're going to be maximizing over lambda. So this is the function, this is our d of lambda that we're going to be optimizing. And this is, as I mentioned earlier, this is the minimum of our Lagrangian over the primal variables, and therefore it's the minimum of this objective. So how can we use this for optimization? Well, the first step is that we can actually compute this minimum in closed form for each function, for each value of lambda. So this is a quadratic objective, and it has a single minimum over theta and theta 0, and we can derive this in closed form. So we can derive an expression for theta in closed form. So we can take the derivatives of this quadratic function, we can set them to 0, and then we can solve for theta. And if we work out the math, I'm not going to work out the math in these lectures, but it's just straightforward algebra, straightforward calculus and algebra to set this derivative to 0, solve for theta, and then we will, well, if we set the derivative to 0 and then so the derivative is going to be the gradient. The gradient will equal 0. The gradient is a vector, and that will give us a set of equations. And from these equations, we can derive the following. So these equations have to hold. And one of these equations happens to be an expression for theta. So given that we have an expression for theta, which is our, again, this is our minimizing theta, we can take this and we can plug it into the objective function that we see here. And if we plug it into this objective function, everything simplifies, and now our expression for this objective has the following form. So this is the result of taking that expression for theta and plugging it in back into the Lagrangian. So now this expression, this is the solution to this optimization problem, but I have solved for theta directly, and so for any lambda here, this is the expression for the Lagrangian with the optimal theta and with the optimal set of parameters theta. This is going to be this form. So I have derived a closed form expression for d of lambda. And now the only thing is, in addition to having this form, I also have to make sure that the lambdas are always positive, and that the following constraint holds. So this constraint, we saw that it has to hold for in order for. So we derive this by setting the optimal theta. So when this theta is the actual minimizer, this constraint must hold, and therefore we also must enforce it as part of our dual optimization problem. So now maximizing this over lambda gives us the dual optimization problem. I have defined a dual version of the SVM problem, and this is how it looks like. Now, recall that in the Lagrange duality for SVMs, we know that the maximum of the dual is less than or equal the minimum of the primal. But it turns out that in the context of SVMs, we can show that these problems are indeed equivalent. So they reach the same minimum, the optimum of each objective, the optimum of each problem achieves the same objective value. And so here, this is one of these cases where these two problems are actually equivalent, which means that now the dual of the SVM is something that we can use to formulate our problem. Now, let's look at a few properties of the dual. We can make a few observations over this. The first observation is that this is, again, a constraint quadratic optimization problem. So this is a reasonably good form. Quadratic optimization problems are ones that we know how to solve. It's also interesting that now our optimization variables are the lambda, and let's look at how many lambdas we have. We have exactly n of them. So we used to have n constraints in our previous problem, and now we have n variables, where again, n is the size of our training data set. And finally, one observation here is that this objective, it depends on our data x, but it only depends on the dot products between the different x's, which is quite interesting. And we're actually going to revisit this in the following lecture. And this is a property that I'm just going to briefly mention here, but we're going to come back to this in much more depth in the next lecture, and we're actually going to see that this is a very, very important property of the dual that is going to unlock an entire new set of SVM type algorithms that are going to be very powerful, and that they're going to be a very important set of algorithms in machine learning. But for now, I will just leave it here, and we're going to look at certain other aspects of the dual first. So we have defined a dual and a primal. And how do we know when to solve the dual or the primal? There's going to be multiple reasons, but I'll start with two for now. So first, notice that the dimensionality of the primal, at least in terms of the size of the variables over which we're optimizing, it is linear in the number of features. So the number of optimization variables equals to the number of features. There's d of them. And so if we have a really large data set with many data points, then we should focus more on the primal. However, if we have a lot of features but less data points, we want to use the dual. And so, for example, if we want to do some kind of polynomial expansion, then we can do this using the dual version. So if we have a very large number of polynomial features, if we have a polynomial of really high degree, our number of optimization variables does not depend on the degree of polynomial. of the polynomial features that we use. And so potentially we could use a very large number of features in the dual, but still the complexity of our optimization problem will not increase as we add more features. So this is an important property that we're going to be revisiting later. But for now, I want to pause here with the definition of the dual, and then in the next video, we're going to look at how we can actually solve this dual, and we're going to look at a few additional practical aspects of this dual approach.